Hello and welcome to our fourth video in the series. In the last video we did some von Neumann analysis to show some instabilities that we have in R. In this video we're going to be doing we're going to be using the Crank Nicholson method. This will give us some versatility with our R that we can use for our analysis, and then we're going to do some coding at the end. So in our previous videos we said that we can write our simplified heat diffusion equation like this for the von Neumann analysis. So what we're going to do in the Crank Nicholson is we are going to express this as a slope. So we're going to take our current in our previous, and then we're going to divide them by 2. So I'm going to keep my t to the j n plus 1 minus t to the j n on this side just to make it easy. We are going to have our alpha delta t delta x squared. And since we're going to be dividing this whole thing by 2, I'm just going to pull it out from the start so that it's just easier to work with. And we are actually going to just call this R. There is that 2 in the bottom of there, but we'll get to looking at that later. So we're going to say that that's R. So we're going to take t to the j plus 1. We're going to say that n plus 1 is our current time step, so then our n can just be our previous time step. Needs to be a t there. N plus 1 plus t to the j minus 1, n plus 1. And then we're going to get our plus our t to the j plus 1 n. So these are our previous time steps. Right? Next thing we're going to do is I'm going to multiply this r through this whole equation. So we're going to get forgot to add the r. It's the whole reason we're rewriting this long equation. Okay, so now that we have this, I'm going to separate our like terms. We're going to put all of our n plus 1s on one side, all of our n's on the other side, and then see if we can pull it out or simplify it easier. So we're going to keep our t to the j, n plus 1 on this side. We're going to subtract this one. Add the next term. Minus our next term. That's going to equal, we're going to add this to the other side. Plus rtj plus 1 to the n minus r2tjn plus rtj minus 1 to the end. Okay, I'm going to pull out our, well, we can look at these. And then we also have that over here. So let's one more time. We're going to have that negative r we're going to get 1 plus 2r. We're going to pull that t, j, n plus 1 out. Minus r, t, j minus 1, n plus 1. And then we're going to do the same thing for the other side. And plus our r, t, j minus 1, n. Okay, so now that we got this far, we are going to look at this using some matrix math, and see if we can simplify this easier, since it is a little bit more complicated than our previous equation. So we're going to go to that now. Okay, so we have I kind of set up the outline of our matrix. We're going to start this, we're going to do our middle column. This is going to be our t to the j. This is going to be our tj column. So we'll have t when j equals 1, t when j equals 2, all the way down to t when j equals 98. Now we do have some boundary conditions on here, like when j equals 0, we know that the temperature of this is 350, because in our previous example of our bar, we had one end where we had heat coming in at 350 degrees Kelvin, and then at the other end, so at T where J is at 99, position 99, our temperature is 400 Kelvin. So from here, we're going to put this in our matrices, we see that when the position is not changing, it's being affected by 1 plus 2r. And we see that negative r is affecting both of the previous and the current ones, both of those. And what we see is as this thing is like oscillating down, we're going to get this really nice diagonal. So from here, we need to figure out how to fill in this side. So we're just going to plug in our 1 for each of these into this side. So we're going to get that r when t equals 2, or when j equals 2, not t, plus our 1 minus 2r of t where j equals 1. Uh-oh, I write too big. I want to keep it like lined up. Okay. Plus our r of t 1 minus 1. That's going to be where j equals 0. And then we're just going to keep doing this for all of these. And we also know we'll get r t where j equals 3. J equals 2. So, and then again, this will go all the way down until we do our t of j 99. We do have these little boundary conditions out here. So this is going to be, we are going to grab it from this one. So plus r t when j equals 0. And then we'll also get plus TJ equals 99. Because for the first time step, we have to add those in there. And this one will come from this one. Okay, so now that we have expressed it in a matrix, in a beautiful this diagonal, which is really going to be helpful when it comes to coding. So that's what we're going to go do next. We're going to do our coding and see how this changes and see what we can find. Okay, so now we are on to the coding section of this question. So the first thing that we need to do, we just found our matrix. We did our Crank Nicholson method. So the first thing that we want to do in order for our matrix to show up, we have to, from SciPy, we're going to import solve banded. Oh. Okay. So this is the same code that we had already from our previous videos. So we're just going to add to it. Oh. No. What am I doing? Okay. And that's the graph that we got last time. So what we're going to do now is, so since we're using the Crank Nicholson method, we're showing that R has some stability above 0.5. So we're just going to say that our R equals 1. Next thing we want to put in is our temperature array, NX, and 300 is our initial, what this whole bar started at. We got to put in our boundary conditions. So when t is 0, we know that that side of the bar is at 350. Oops. And on the other side of the bar, on the right side of the bar, it's going to say t of -1, where this equals 400 Kelvin. Oh. Okay, the next thing we want to do is we want to figure out how to put this matrix that we just found into our coding. So we're going to call this matrix A. And because there are columns that were zeros, we're going to use NP zeros, where we have three diagonals and x minus 2. And then those will give us our boundary conditions. Since we had one at the top, or one at the left and one on the right, we just want to take those off. From here, let's say what our diagonals are. So our first diagonal is going to be that -r. It's going to go from 0 all the way through to the end, and we said that that's -r, not range. For a to the next position is going to be 1. Ooh, we need commas up here. And this equals that 1 plus 2 times r. And then a for our third diagonal, again, that's just going to be that -r that we found. All right, so from here, we have another matrix that we want. We have to get the other side of that equation. So we're going to call that matrix B. MP zeros and x minus 2. Now let's say what that B equation is. So when we were plugging it in, we know that it's R times our temperature to the left plus 1 plus 2 times r times the temperature that's in between our bounds. And then plus r times t. And then this one's to the, oops. To the right. So this one is going to be 1, 2. Okay. Now we do need to set up our boundary conditions for B. So when B is 0, it's going to be that 350. But we're going to say it like this because this one does change. There is that add the plus r times t of that boundary. Oh my goodness. And then our other boundary is at that -1. It's on the other side. And it's going to be the same thing in here. Plus, there it is, r times t to the -1. Ugh. Shifting on the wrong times. So we do want to see this in a plot. So we're going to call this Fig 2. Fig 2, we're going to make subplots. And we got to add, scatter where x equals x, y equals t, and we're going to name this thing T profile. Oops. So from here, oh. This should be a multiplication sign. Okay, let's see if that fixed it up. No. R times t to -2, or 2 colon, plus 1 plus minus 2r times the t in that. All right, let's try that. Let's just run it all. That's why. That's supposed to be a -2. Okay. Oh, Fig 2 equals make, underscore subplots. All kinds. There we go. And then, so for this, we want to, so for I in range, we're going to say that we have 3,000 time steps. Colon. And this t, this is where we're going to put our solve banded in here. So from our bounds equals our solve banded from that 1 to 1, and then our A and B that we just set up. We need to re-copy down what our B equation is and what our boundary conditions are. So give me a second. Let me do that. Copy that. Oops. I'm gonna paste that right there. Let's get rid of those extra B's. I'm gonna make sure this is all aligned. Wonderful. So now that we have there and there, we do have 3,000 time steps. So we're gonna change that to just show every 100 time steps, just to make the graph a little bit cleaner. Colon. Oh. Wow. From here, we want our fig to scatter for x equals x, y equals t, name, and we want this figure to show. Fig2.show. All right, so let's run all of these and let's see if we made any mistakes, or let's see what we get. Uh-oh. Oh. There we go. Okay. That was not what we were looking for. Oh, it's because I did my time steps at every 1,000. There. Still not pretty. Still not what we're looking for. Why? Let's just run all. There we go. All we had to do is run all. So the cool thing about the Crank Nicholson method is that in our previous plot, we saw some instabilities up here when r was greater than 0.5. We got these extreme values all the way to infinity, super high. But in this case, our r is 1, and we have this beautiful looking graph. We can even, let's do 6. Let's just see what we look like. Okay, so we see that it's still a pretty nice graph. It does have some inaccuracies in it, but it's not as unstable. It's more stable than our von Neumann expression that we did in coding. So let's change this. Oh no. Okay, so I'm not sure what I did. But you saw the plot. And so that's why the Crank Nicholson method is so more powerful and more useful when it comes to demonstrating the evolutions of temperature with respect to time, like with temperature over time. So I do think that this concludes our last video, and I hope you guys had a good time.